If you have chemotherapy, you are given the drug throughout the body. This, unfortunately, carries horrible side effects with it because you are effectively poisoning the entire body. So one of the holy grails of drug delivery is to try and target the drug. You want it to only go to the tumour and not affect the rest of the body. We can do that within a bubble, but then of course you need A, to get it to the right place, and B, to release it when it gets there. We are trying to engineer the coatings on microbubbles to make them more detectable. Bubbles make fantastic vehicles for drug delivery. We have this core of gas, we have a coating. That coating acts as a scaffold. We can put drugs into that, we can put DNA onto that in some cases, and we can add ligands, targeting species to the surface of the bubble that will actually go and bind to, for example, cancer cells. Bubbles must not block blood vessels. All deep sea divers, all astronauts know this. The smallest blood vessel in the human body is about 6 to 8 micrometers, so that's a millionth of a meter. It's about a hundredth of a human hair. Our bubbles have to be even smaller than that. They have to be about 1 to 2 micrometers. Generating bubbles one by one on that scale is quite a challenge, and the devices that we produce in this laboratory are aimed to do that. One of the strategies we're trying is to make the bubbles magnetic. So in addition to the drugs, whatever else we're putting in the bubble, we put magnetic nanoparticles, and this allows us to steer the bubbles using a magnetic field. Because we can track bubbles under ultrasound, we can monitor where they are in the body non-invasively, and once they reach a target site, again with ultrasound, by increasing the power, we can pop the bubble open and release the drug just in that local area. So we are only treating a very, very small volume of tissue. We don't have to treat the whole body. So at the higher end of ultrasound imaging, we're turning the power much higher than you'd use in a diagnostic scan. You can actually deposit a large amount of energy into a very, very small volume of tissue. That in turn creates a temperature rise that can actually destroy tissue. You're effectively cooking it. What showing here in a little gel phantom that mimics tissue, it has similar properties as far as the ultrasound is concerned. You can see this region has turned white. That means that it's been denatured, it's been affected by the heat. And if this were in the body, this region of tissue would have been cooked, because as you can see, the surrounding tissue is completely unaffected. So this is a new technique that's being pioneered for cancer treatment, because it can be done with a large ultrasound transducer that is outside the body without the need for surgery. Seeing something you've produced, something that you've created, actually being utilised, I think is really, really exciting.